So, any questions or anything we need to deal with first, or can we just continue with our interference graph for real? I really want to finish this today because I would like to talk about the next section because that's the first thing you have to do for the project. I heard some rustling there. Anybody who's going to say something? Right. Well, then let's jump into it. We can always take questions in the end. Let's just see. She's not. All right. So we left off. I sort of gave a hand wavy definition of an interference graph. So let's just do it properly. So if we say, let's grab some instructions and take any of those. And we'll have some variables. We'll take m of those. And let us, we'll create a control flow graph G. And so we just say that Li is the same as live out II, just so we don't have to write too much. Actually, I need to just rename this stuff up here. So we need to create a new graph. We'll call that one G, which is very original. And we'll call those V's and E's, also very original. And we'll say the vertices are my variables. Oops. And then we'll say that an edge between A and B, actually should we say VI and VJ, is in E if and only if there exists a K such that VI is in LK and VJ is in LK as well. So in other words, when we create this graph, the edges, we can say there is an edge between variable VI and VJ if they both exist in some live set. Because remember last time we looked at that and we said, right, if they, let's see, do I actually have that somewhere? I probably do, right here. Yeah, we actually, so we had this little example and we said, you know, if we looked at this here with V, Y, and Z in the same live set, then we couldn't use a register to have we couldn't use the same register to house V, Y, and Z because they're live at the same time. So that's the interference graph, and you know we did the coloring last time, but we'll do that properly as well. Now we should also just define chi of G, which is the chromatic number of G, which is the smallest number of different colors needed to color G such that no two neighbors are the same color. Now we know that finding that is NP. We know that a trivial upper bound is delta G plus 1. And of course, delta G here is the max in degree. Actually, it's just max degree, right? Of any node. So basically, we're looking at trying to find something in between. So what should we call that? N, such that we can't do better than the chromatic number, and we can't do worse than that. Okay. So what are we going to do? Well, we're going to start by find the node with the smallest degree. Color it a new color. Remove all neighbors and edges to them. Actually, I think we're going to have a step 0 up here that says pick new color. Then we'll just say color it here, because now we can go if more nodes left, go to 1, else go to 0. Now I know the way that I wrote this, it's never going to terminate, but you know what I mean. So what we're going to try to do is we're going to try to divide the graph into subsets of nodes that all have the same color. And I'm going to try to make such a graph. And I'm going to try to make it look nice as well. I'll copy that. I'll put one there. And put one there. Put one there. 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 And there. That wasn't too bad. And then we need some straight lines. Actually, we need some. So that's A. No, it's not. That's C, A, B, D, E, F, G, and H. And then we have some lines, which I shall try to make nice and reasonably straight. It's not perfect, but it's the best you get. So let's say that we had something like this, where A, B, C, D, E, F represent variable names. It could be the names of the variables. So now let's give it a go. Oops, that one. we'll copy that. We'll paste it there, and maybe we'll make it a little smaller. Actually, what I'm going to do is I'm going to make a copy of that. Just put it there because we probably need it. Right, so we start by picking a color. What should we pick? Green. So we'll pick green. Now we got to color the node with the lowest in degree. Which one is that? Well, it's that has 2, that has 2, and that has 2. So pick one of those. We'll pick A. So we're going to color. Now you can't see that it says A anymore. But what we can do is we can say U1 is equal to A. Right, then what do? Well, we remove all the neighbors. So that's that one and that one. And that means we get rid of those and those edges as well. So if we do that, we gotta do get rid of that, get rid of that, that, and that. So we're left with this. Now pick the one with the lowest in degree, color it green. Well, that's got to be this guy here. And you know that was supposed to be a capital A. So now U1 is capital A and capital D. Right, so now when we remove these neighbors, that's fairly easy because there are none. So we end up with, if I can do this, no, if I did it with the lasso, there we go. So we get this. What should we pick? The lowest degree, that's either G or F, so I'm going to pick G. So we'll copy that in, and U. Now my pen stopped working. U1 is A, D, what was it we call it? G, I think. So we need to remove those, and those, and we'll be left with that. That. And we have this, and now we need to delete those, and those. So that's easy enough. Now we can color this one. And then we get U1 is A, D, F, and G. So if I take this guy here now, and we then say remove U1 from G, because we've already colored all of those. Those are the ones that are going to remain green. So that one is green. That one is green. That one is. And that one is. All right, so let's go here. Right, so now we got to remove that, and these, this, and those. So we end up with that. All right, let me just make a copy of that. This is a nice thing about the iPad. You can do this. You can't do this on a board. All right, we need to pick a new color. What should we do? Red? There we go. Lowest in degree, that's got to be this guy here. Yeah, so U2 is a C. Right. So remove all its neighbors. There aren't any, so that's easy enough. So we just copy that. So there we go. Now, which one should we pick? I picked B. Could have picked H as well. It doesn't matter. So U3 is B and C. Then we remove that and that and that and that, which means we're just left with H. See if I can figure out how to copy that. There we go. So we remove that. We can color that guy, and we'll get U3 is ECH. Now let's bring that one back so we can see how far we've gotten. Copy that. Paste that there. And then it was, what was it that we colored here? We colored C. Oops, that's not a color. We colored C, B, and H. So just like we removed U1 from G, there, so okay, if I remove U2 from G also, then I end up with, so that's out, that's out, that's out, that's out. We end up with that. All right, pick a new color. Color it. U3 is E. So we can say that V is U1, U2, and U3. And that one, of course, was whatever it was, but that makes sense, right? So we can finally take this guy, put it here, and paint that one. I don't know if we should just put some numbers on again. A, B, C, D, E, F, G, and H. So if we did it right, we should now have colored this in such a way that no two neighbors should what be U2? Ilya, what were you asking? For the reds, you have both U2 and U3. I do. That's wrong. Both spotted. I got carried away by going up by one there. That should be 2. 2. Yeah, got it. Thank you. So none of these neighbors have the same color. So this means that 3 registers will be enough. We can put the ones that are in U2, or sorry, in U1 in one register, the ones in U2 in another, and the ones in U3 in another one. Now, let's try another one. So I can show you something else. So we need a node. We need a few of those. There. There. there, there, and there. And we need some lines, so let's see if I can remember how to do that. There, there. These lines are not as nice as I wanted them to be, but that's alright. There, 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 there. This almost reminds me of that train subway shuffle game. So we get something like that. I need one more here. And this is V, X, U, W, Z, and Y. Right, so let's see. Which one should we do first? We should probably do, probably color X first. Let's see if we can do that. X, and I'm just going to use the transparent colors this time because they're a little easier to see, I think. So we'll start with the transparent green. So we'll color. Wow, that went fast. Oh, it's because I'm using the big one. Right, then what? We'll copy that. We'll put it here, and then we're going to delete that one and that one. That one and that one. And then all of those, and those. Oops, I think I got carried away here, didn't I? I did. Oh, I got carried away from because there was that one is not supposed to be there. That one is not supposed to be there. So I'm actually going to delete that. Make a new copy of this. There. And now I can delete. That's the neighbor, and that's the neighbor. That, and that. So we get something that looks like that. Right. Which one should we pick? We can pick Y. Also, I need to color it, don't I? There we go. And I mean, this is not particularly hard. You could probably be bored out of your mind watching me do this. So we'll get rid of that, and then we are going to color that guy. So now we have oops, X, Y, and W. Cool. So if I remove those, what am I left with? Get this wrong again. So yes, I'm missing something. Sorry. I want something that looks like that as well. Maybe not quite as sloppy. Should we do straight lines? Straight line there. Oops. There. What the hell's wrong with the pen today? There we go. Right, so we need to remove all the green stuff. Let me make a copy of this first. I think we're pretty much done now, so we'll remove that and that. That. There's something really, really, really going weird with the pencil today. That, and that. So we are left with one of these. How many colors does it take to color this sort of thing here? I think it takes 3 at least. 2? Ilya? 2? 3? Are you counting up or counting down? Or changing your mind? Well, If I pick a color for that one, can I make V or U blue? No. Pick a new color. Can I make U yellow or blue? No. So we'll do that. So we end up with, now we just need to make a copy of that. We'll put that here, and then we'll just color those up. What was it? That was, what did I make? What? U, purple, Z, blue, and V, yellow. So, what do we need here? We need 4 colors needed, which means 4 registers. Right, what if I only had 3 registers? Are you going to need colored pencils for the final? I don't know if you can color your laptop all you want. It's not on paper, unfortunately, so no, I think you'll be fine. So what happens if we don't have 4 registers? If you have on a machine that only has 3, I mean, you could always choose to not use any registers, but that might not be an option. So we need to figure out how to reduce the requirements. So we're going to have to look at something called spilling, which is 8 to 5. So if I have something that says x equals y plus z, then we can spill y in the following way. What we're going to do is we're going to load it into a new variable called y1. So we'll simply load the value of y. And now I'm going to say x equals y1 plus z. Now what is that going to do? Why is that going to be different? Well, it's going to be different in the fact that there might be many occurrences of the use of the variable. Oh, now we're getting a call from somebody. There might be many occurrences and uses of y in the code. But if I replace this one particular occurrence of y by y1, now I have 2 different, so to speak, references to y. I have the general y, and then I have this new y1. Hold on a second. I don't know how I set how I can set focus on that one. So if the y we had here was in a big set of other, or maybe even just because it's in here with z, would require a line between y and z. If that's the thing that causes an extra color to show up, we might be able to break that by doing this sort of stuff instead. So maybe spilling something will reduce the number of edges. That's certainly possible. So if I spill a use variable, then I do that by simply loading it into a new temporary variable immediately before use. If I spill a def variable, well, that becomes something like y2 equals that part, and then it becomes store y2 at y. So again, what we do is we introduce a new temporary variable. And the thing about this temporary variable, it pops into existence here, and it's used here, and then it's gone. No, I don't want to stream that call. I know what she wants. She wants to just argue about something. My friend from Texas. I'll give her your phone number. Right. So let's see. It says here, now look on page 465. So maybe I'll go back to page 465. Which I think has been turned into page 466, example 5. Oh, it starts here. And I'm going to see if I can take a picture. Oh, this is not going to work well. It's this picture here we need. Yeah, that's not too bad. But we might need to just crop that a little bit. There. Oh, that's not too bad. Right, so if we have something like this, and let's see, what variable should we try to do? So there are 3 instructions referring to v. So can we just highlight where that is? There is something that refers to v there, and there. 3, 4, and 7 is what I have. Where's 4? Oh, it's there. So we have 2 uses and a def. So if I want to spill let's spill v, right? So what does that mean? Well, let me take a picture of this, and we'll move it over here. We'll just make it a little smaller here. So for I3, spilling v there is the spill of a use. So we have u equals w minus v, which becomes v1 equals load v, and u gets w minus v1. We have I4, which is v equals minus u. So that becomes v2 equals minus u. And then it becomes store v2 at v. And I think we got one more there, number 7. That is also a use, so that's y equals v times z, which becomes v3 equals load the value of v, and then y is v3 times z. So if I do that, we get, and now it's picture time again. We get this thing here with hand corrections and everything on, but we'll live with that. So we'll just sort of sort that out. Oops. There. There. Why did that not work? Oh, I probably forgot to say okay. There we go. So what we can see here is that we have added, we have transformed that, we've transformed that, and we've transformed that one. Now that last one is a little difficult to see. So now I can go through and recompute live sets. And if I do that, then I think this graph is the one we just saw, right? Yes. Yeah, so that's that was this guy here. So let's try to create the new interference graph. So maybe I should just make a copy of this one here and carry with me. We'll put it there, and then we'll say that's the old one. Now if I do this again. Then I'm just going to go steal this guy here so it looks sort of the same. Because if we think about it, V disappears, so we should be able to just chuck that one out. But we get a V1, which is associated with W and Z. So let's see if I can actually, maybe we can steal that one. I'll put it here. That's not entirely how I wanted it, but close enough. We need that gone, we need that gone, and then this is V1. We need a V2 and a V3 as well. We might as well just steal a copy of that. And I'm going to try to position them somewhat strategically. How about that? Go. And this one is V2, and that's V3. Let me a straight line. There, 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 and there. So I get this graph now. Now, what's the chromatic number for that? I don't know. What should we call it first? Let's do X. What color we started with? We started with green, didn't we? So that one, right, what can we do then? We can remove that, those. So we end up with something that looks like this. What should we pick there? It doesn't really matter, but I'm going to pick the same as I picked in the book. So we will take V2. That's this guy here. Cool. Then we can take V3. There we go. And then let's pick Y. There we go. Now we do some erasing. That one, and that one. And what do you want here? W maybe? We'll pick that, and we will remove that. So U1 is W, X, Y, V2, and V3. Now we're just going to grab this guy again. I don't know why I actually think this is fun. It's like doing puzzles. So we do that, and we remove those guys then, and then we try it all over again, right? So cool. Remove X, and we remove Y, and we remove V3 and V2 and W. So we end up with that. We'll go red. That's not red, but close enough. Actually, is there a proper red? So we'll pick those two, and that'll end up removing that. And now we had that one left, which I shall. That's not right. Oops. That's not right. I got carried away a little there. We end up like this instead. And then we can color that one yellow. So there we go. So all in all, we get Z. If I can get my colors back, colored yellow. We get W1 and U are red, and the rest are green. Right, so what on earth does that mean? Oh, we should just write down that U2 is U and B1, and U3 is just that. So only 3 registers are needed because we have 3 colors. So it looked like we made things more complicated, but by adding more nodes, we broke some connections, and you can see what really happened here if we look at it is these guys here are only connected to Z, whereas when they were represented by this V, they were connected to, well, what were they connected to if we look at the original one? U, V, Z, Y, and X. So for these temporaries here, we broke an awful lot of bonds, and that's why we can now color it with less or with fewer colors. Now, what's the downside to doing this? Anybody? Well, think about what happens in order to do this. So when I decide to spill a variable, regardless of whether it's a use variable or a def variable, I have to interact with main memory. So there's a load in those two situations, and there's a store in that situation there. So I do have to interact with memory. If I'm spilling, then I'm loading it in at the last minute before I need it, and I'm pushing it back out as soon as I possibly can. So when you pick something to spill, then it probably might be a good idea to pick something that isn't used very often, but in a strategic manner. So we could spill variables with few definitions and uses, but if you only have few definitions of uses, that might not actually give you anything. We could also try and spill variables with the most number of conflicts. I mean, if we had all the time in the world, we could try to actually go through this and see what's the best we can do if we try to spill every single one of these variables. It would be very interesting to try to do it with Z, because it has really, really many interactions in here, it looks like. So if you're bored when you're done with your phase 6 tomorrow, then you could give this a go for all of the variables one at a time, to try to see which one is the best one to spill in terms of how many colors do you need, and how many extra memory accesses do you get, because those two have to be weighed against each other. And in general, it's probably not a good idea to spill things um, that are variables used in inner loops, because they're used over and over and over and over again. That means access to main memory over and over and over again. So, but those are all just heuristics. There are no, if we knew exactly how to do it, we wouldn't have anything NP on our hands, right? Well, I'm sure there are people that are almost done with phase 6. Right, so enough about register allocation. This is how you do it. This is how it's done by real compilers as well. But we don't have to worry about doing that in the Espresso compiler, because, surprise, surprise, the JVM does not have any registers. So at least that was a dead end. It's cool to know and understand, and I think this is really interesting because it brings in so many different disciplines of what you learned in other courses as well. But now for the first part of phase 6. Something that you cannot say 5 times fast if you're half drunk. Activation record address allocation, or address assignment. Now, let's just take a look at an example to begin with. see what we got. Double W. What is on the next page? Nothing. All right, cool. Right. So when this f function runs, or f method, we need an activation, right? So this is an activation record for f. And this activation stack is, of course, 32 bits wide. Now we have, how big is this activation record? So how big does this activation record need to be in order to hold what it needs to hold for that f that I just put there? How much data do I need? How much space does the integer x take up? 32-bit, so one spot, right? So what about the double D? 64-bit, so it takes up 2 spots. If the stack is only 32-bit, we'll have to break it into most significant 32-bit part and a least significant 32-bit part. What about int a? Well, the same thing, and then the double W is also 64. So we're at 64 times 2. We'll just count it in words instead. So 6 words of 32-bit each. What about this? Does this function have a this? Jonathan says no. Why not? Why does this not have a this? That's not confusing at all. Is it static? Or is it non-static? Non-static, Ilya says. Do non-static methods have thises? Or do non-static methods have a this? I think is probably the right thing to ask. Yes, they do. So if non-static methods have a this, does f have a this? Yes, it does. Because if it didn't, then since it's non-static, it can refer to non-static fields. And if I don't have a this, then I don't know what those non-static fields or where those non-static fields come from. So, hold on. Oh, that's not going to happen. It'll come in a sec. So at 0, we have this. This is always at address 0 if it's there. Then we can do this. We'll put int x there. And at 2, we'll put double D, but that takes up double space, so that's 3 there. 4 is now int a, and 5 and 6 will be double W. Right. So here's what we can do is, we at some point we got to go through this code and see and say every time I refer to this, this, and this, I have to associate with it an address, because the variable names are going to be gone in the bytecode. So we can simply do it by just saying, right, if this is a non-static method, then start counting at 1. So do the following and say, right, we'll give this one address 1. So that's our counter. So for non-static, start counter at 1. So here's my counter. So we've used 1, so we increment by 1. So now it's 2. Right, that one gets 2, but it's a double, so we increment to 4. That gets 4, we increment to 5, and that gets 5, and then we're done. But we could increment that one to 7 so that we know that we've used 6 spots, or we actually use 7 spots because it's a non-static. 0 counts for 1. So if I were to say go and implement this, which actually I do say go and implement this, then we might just note here for static start at 0. So if I put the word static there, then we could have gone 0, 1, 3, and 4. Because there is no this, therefore we might as well use spot number 0 rather than leaving it unused. So what's the easiest way to allocate addresses in such a way that every variable and parameter gets its own spot without taking anything else into account? Well, it's just do this. Start the counter at either 0 or 1, depending on whether the method that you are address allocating for is static or not. And then plow through it. So in visit method decal, you say, hey, if you're static, set my counter to 0. If you're not static, set my counter to 1. Visit the children. Now, which children do we then have to worry about? Well, we have to worry about param decals and local decals. What do they need to do? Well, they grab the next available address, and then they increment the address by 1 if it's not a double or a long, and 2 if it is. And there we go. That's how you do address allocation in the most simple, straightforward way. We can do a little bit better. So for example, and somebody's probably right now thinking, wait a minute, that sound this sign sort of sounds or smells a little bit like what we just did with register allocation, because what if I looked at these spots here, as registers, and then I say, are there any of these variables that don't exist at the same time? Then maybe I could make them share a spot. And yes, you're absolutely right. You could do that, and you could create an interference graph. You could do all that hullabaloo as well, if you wanted to. I just want to show you a better, but again, not a perfect way, but a very simple way of doing better. So we'll throw in a couple of parameters. We'll throw in a local there. We'll throw in an int. Should we do another int here? Something like that. Now, if we did this sort of with our head under the arm like we did in the previous one, we would say, actually, should we do that in so? Like before, this one here is at address 1. It's a double, so we're going to go to address 3. That's a double, so that goes to address 5. That's a double, address 7, and address 8. I think that's correct, isn't it? I think that's correct. Now, what can you say about the relationship between D and A and B? Can I ever create an expression of any kind that involves D and A at the same time? What do you think? So can you write something in this code anywhere in it where I legally have the expression say d plus a? Where would you put it if you can? After a, here. So something d plus a. Is that where you want to put it? I assume that's where you want it. Right. Now, if I do the following and I say, I don't know. So if we color the scope of D green and we color the scope of A, oh, I don't know, should we take the purple one? I like that one. That. All right, what's the scope of D? Well, it comes into existence here, so its scope starts there, but it ends there, doesn't it? So the scope of D is sort of this stuff here, right? And what about scope of A? Well, it starts there and then it ends there. So it's got to look something like that. Right? So, no, you can't. Well, okay, they're not in the same scope. If they're not in the same scope, then they never exist at the same time. They definitely, if you did the interference graphing, you would realize that they're never live at the same time. There can't be a live set in which both A and D exist because they're not even in the same scope. So if I look at how I would lay this out, then we get this at 0. At 1, we get AA. At 3, BB. At 5, D. We're going to need just a little bit more space here. At 7, A, and at 8, B. But isn't it true if I say that and those are not in the same scope? So reuse 5 and 6. Because what we do is, let's try to do this in a better way. We start out, so we'll do a better way where we reset after a scope closes. Because anything that was allocated in this scope disappears here. So whatever the counter was here, we can set it back to what it is there, right? So we can say what the counter is here can be reset to the same here. So again, 1, 3. So it's 3 at this time. So we get 5 for that one. But now we reset back to 3. So we get, 1, 3. It's 5 here. And it's 5 here. This one becomes 5. And this one becomes 6. And then, of course, we can reset back to 5 here if there were other stuff. So we can reuse things that died when the scope closed, basically, right? Now I don't remember what the reference compiler does. Is there anybody here who has installed Phase 6 already? Cool. Now, will you do me a favor? I'm going to share my screen with you. If I can figure out how to do that. Right, so let's just try writing this program. Oh, would you look at that? I already had a test 121. So we'll try test 122. I should make a little booklet called "The Best of Test." Here we go. Public class 125. Public void F. Double AA. Double BB. And then we'll say double D. And then we will say int A, int B, and we'll do that. And then we'll say espresso C. Oh, we just have to, I just got to fiddle something with that one. Just now, oh, it's fine. I don't need to see the type checking information. Espresso C, test 125. Oh. Public class 125. Oh. Shall I call it test 125? Yes, really edited. There you go. Yes, save. Yes. There we go. Save. Yes. Save, save, save. There we go. Espresso C test 125. There we go. More test 125.rg. So maybe I should just say a few words about this. When you get the output from the reference compiler, there is a ton of comments, and you can see that's all these guys here. And that's really helpful if you're using it sort of as a support system. But if you just want to see the code, you can say grep-v test125.rj. So if you do that, you're grepping all the lines that don't start with a semicolon from that file. And .rj is the reference compiler, and .j is your compiler. So that one now says 7, and actually, if we look at the address allocation here, it says 1 to AA. I think that's what we had here as well. Let's just check. Yep, 1 to AA, 3 to BB. Yep, 5 to D. Yep, 5 to A, 6 to B. Yep, yep. So that's what my compiler does. Could you run? I have a feeling that your reference compiler is slightly different. Could you somebody run this same code and just show us what the address assignment actually spits out, so that we know which one the reference compiler implements? Because if the reference compiler you have implements the old-fashioned linear kind of way, you should do that as well, because otherwise it becomes impossible to do diffs. So somebody type that in, run it through the reference compiler, and let me know what comes out. Waiting. What was the code again? Are you sleeping, Spencer? Wake up. That or that? Take your pick. So now it all boils down to how fast Spencer can type. Without making mistakes. Suppose I could try to install Phase 6, see if I can do it faster than he can type it in. But I don't think I can. No pressure, Spencer. No pressure. At all. Do you think he left? Ilya, he's your responsibility. You gotta go find him. It's not like you have 35 people waiting for you or anything. So, by all means, if you need to go to the bathroom as well, that's fine. All right, the race is on. And I can't even spell. There we go. Ah, he made it. 1135. Okay, so the reference compiler actually does the slightly smarter one, but that's not very difficult to implement anyways, because all you do is you make a note of what the counter is before you start a block, and then when you're done with the block, you set it back to what it was. That's the only difference, and it will save you. It'll save you a little bit. Cool. Then we are now at 8.4, the JVM, which actually, you know what? Let's do that next time. Let's say we did good for today, and then we can spend the rest of the time if anybody's got any questions about anything. Oh, I do have one thing. Are we going to do a review thingy on the weekend before the exam? If we are, then it's going to have to be Sunday morning-ish, because I am unavailable Friday because I'm flying Friday. I managed to get my hands on a very expensive ticket. You might as well post it myself. Plane tickets are so expensive. But I'm going to be doing it from London, which means that I'm going to be 9 hours ahead of you guys, which means that we probably don't want to do it too late, my time. So let's say we did it. So if we did it at 10 o'clock, is that too early on a Sunday? It is a little early, isn't it? Who's up at 10 o'clock on a Sunday? I'm with you, Spencer. Suppose if you have kids and stuff, then you are, but or pets, they'll wake you up. But yeah, so Sunday 10, 11 ish. 12 is going to be 9 o'clock. That's a little late. If normally these things take a few hours, so that means that I'm going to be going until after midnight. I really don't want to do that. So I would, if we could do 10. So Ilya, if you can call Spencer and make sure he's awake, 10 at least 10 minutes earlier, then we can do that. Or you could have a sleepover, but no partying. Right, so let's tentatively schedule it for Sunday at 10 o'clock here, which is 1900 in London, which is 7 p.m. So that's perfectly fine with me. And the exam is on the Monday from 6 to 8, I believe. Right. Anything else? I dread to ask if there are any Phase 6 questions, because by the look of it, Spencer is the only one who's downloaded it yet, who actually ever tried running it. So, really, is this a Sunday before the exam? It's the day before the exam. Yes, indeed it is. I mean, we could do it on the Thursday before, as instead, if you prefer to do that. But normally people like to get it sort of towards the end so they can sort of polish off, any last minute questions they have. So I think we'll stick with that. I mean, we do have office hours on the Thursday anyways. So if you have anything, you can always come by there and ask questions. Right. Is there another? What does Chili say? Is there another file you come in to study for Phase 6 before implement generate code? Well, you got to do the address allocation first as well, right? If you don't have the address allocator run, oh, okay. Well, yes, there is, because so let's just Spencer, I'll come back to that in just a second. Let's just take a look, because there's a lot of new stuff. So you're going to have, I don't know why I have class files there. You're going to have, you probably don't have analysis in CFG, I can't remember. You have code generator, you have instruction, and you have Jasmine. In the instructions directory, you have to look at this one. You really, really have to. Because if you don't, then you don't know what the various things are. I mean, you look at one of these, oh, jump instruction. Yes, that's the one I create if I'm doing any jumping. So all the instructions that are jump instructions probably use that one. IINC, well, that's probably for the IINC instruction. That's probably fine. Label, well, that's probably for labels. So you see, there's simple instruction and there's instruction, and it turns out that instruction is superclass of everything, but also the one that's used for all the instructions that don't take any arguments. So all the subs, the muls, the divs, the rems, the underscore loads, the underscore stores, all the something to something, all the constant loads, all the returns, etc., etc. So if you don't have if you don't take in any arguments, or if you don't have any arguments in the instruction, so there's an opcode and that's it, then it's just of type instruction. Simple instructions are the instructions that consist of an opcode and an integer operand. So 99% of all the instructions you need is going to be one of those two. And so I would just sort of look at these and say, what are these various things used for? And I think in most of them, there's some stuff up here that tells you. This might not be completely correct, but if you look in the Jasmine directory, there's a runtime constant. That's all the instructions, OPC underscore something. And then there's the representation of what a class file looks like. So for every class, we create one of these, and it consists of fields and methods. And you can see that a method consists of a vector of code and then a link to whatever class body decal it is. You can add instructions, and you can get the code out, and a field consists of a field decal. So as we encounter these things, they get injected into into this class file. Every time we see a class decal, we start a new class file. Every time we see method, we start a new method. Every time we see a field, we put a new field in. And then once oops. Once we're done, we call this write files thing that will then spit everything out in the in the .j file or .rj file, really, whether it's yours or mine. So you can see here's where it creates some stuff that looks familiar. When you do the address allocation, remember to set locals used for all your method decals, otherwise you get garbage. So Shilly, that's a good place to start. Familiarize yourself with those things. Spencer says, I do have one, but I gotta share my screen for it. It's about the output when you have a test file that is just like class main. Public class test for class main. So just like that?
Yeah, like something like that, yeah.
Mm-hmm. So should I compile it?
Yeah, and then like do the like open the main.j for it.
Error. Oh, I should probably say espresso. C. More main.rj. Like that?
Yeah, so when for like the local and like stack allocate for the person like dot limit stack 50 and dot limit locals 1, since there's no method really being called, would you be calling somehow the right method that's in write files inside the class decal or visit class decal?
What do you mean?
Because whenever I tried doing that, like it's not outputted by itself. So I think if there's something specific that we have to do in like inside of like class decal to get the dot limit stack 50 or dot limit locals 1 outputted.
So you don't get anything at all? You just get...
Like if I just use like I get like obviously if I do the espresso CR compiler, I get all that stuff.
Yeah.
If I just do like my compiler, I just get dot class public main and dot super java / lang / object.
Okay.
So and notice because like in the espresso C output like above that, it doesn't there's no method being called. There's only class decal, constructor decal, and C invocation.
Yeah.
So that's why I was thinking that there's something I have to do inside class decal to get that stuff to appear.
Do you get that called?
Yeah. So like I actually let me check. I don't think I do. I get class decal generating code class for main, then constructor decal generating code for constructor for class main.
I cannot type for the life of me today. So one thing I do want to tell you, look, the way I'm doing it is I'm going through and I'm putting all the, I go through the body here, and then I say, hey, if you're a field decal, then go and visit it. That way I get the field decals at the top. And then afterwards...
Is that the field stuff that's being outputted as well?
It's just the order, right? So here I'm just saying if it's not a field decal, then deal with it there afterwards, right? So are you remembering to visit things in your class, in your class, visit class decal?
No, yeah, no. So yeah, that's something. Yeah, so I have to visit that, and then
that's obviously why you don't get them out. Yeah. So if you remember to visit them, then you should get them out.
Gotcha. All right, thank you.
So if there's output missing in your .j file, then it's probably because you forgot to visit that particular thing that you're missing somewhere.
And we won't have the comments like you do on the RJ file automatically, so we can. That's why you recommend we do just like use grep to like eliminate all of them from the output?
No. Let me just send this to Ben so I don't forget. That's not entirely what I said. What I said is if you need to sort of use the reference compiler for reverse engineering, then you probably don't necessarily want to look at all those comments all the time. Then you can remove them by saying grep whatever.
Gotcha.
But if you want to be able to use autogen, or if you want to do just diffs, then you're going to have to spit out the same comments as well. Unfortunately.
True.
And
So AutoGen also tests the compares the .j and .rj files as well that are generated.
I believe so. You see how you can spit out class file.add comment like this. So it's fairly easy to spit out comments because they're if you go and look here, you can see that add comment adds an instruction of type comment, and it puts the line number in and all that stuff in automatically.
Gotcha.
See?
Mm-hmm.
So, I mean, you can choose not to do it and then just, run it and see if it works.
No.
So
Oh
it's
my
working
god.
now. Now
You
it's
got the
working.
donut to work. Oh god.
I got my. Did I? I did.
Oh my
I
god.
Pac-Man as well. All in handwritten curses, kind of thing. Oops. Wow. It ate me. Yeah. How sad is that? Right. One last quick question for the final review. Are you going to send out an announcement on Canvas and Yap? Yes, I will. I'll schedule it in WebEx. And is that a wannabe Pac-Man? That's not a wannabe Pac-Man. That's the real Pac-Man. And it's actually not. It's not finished completely, but it's really not all that long. You just got to put in a little cleverness for the ghosts, and then Bob's your uncle. Anyways, I think we've wasted enough time. So I will see you tomorrow if you come to office hours. If not, have a good weekend. See you on Monday. Bye.